Okay, Chapter 2, Section 1. Weak interactions in an aqueous system, basically in water. What is going on? Well, as I mentioned in the intro portion to this chapter's lectures, we're going to be looking at the attributes of water. The fact that, as you can see here in the figures on the right, that water, even though it is a covalent bond between the hydrogens and the oxygen, those bonds are not truly equal because of the unequal sharing, as you can see in A here. Oxygen has those 2 electrons that it's pulled from the hydrogens, has those more often than not. Thus, it has set up a negative-ish charge around the oxygen. Why do I say negative-ish? Well, because even though those electrons are in orbit around the oxygen most of the time, every so often they will go out and about the 2 hydrogens and then come back to the oxygen. Hence, if you look here at A, you will see that there's the little deltas, delta plus, delta negative. That means that there are poles, a positive end, a negative end, but it's not true all the time positive, not true all the time negative, hence you'll hear me refer to it as positive-ish, negative-ish. So if you have a positive, you have something that's negative, they're going to be attracted to each other. And if one of those things that's positive happens to be a hydrogen, well, you're going to get, as you see here in B, a hydrogen bond. Notice the orientation of the water molecules. Hydrogen in the lower water molecule will be attracted to, not bonding with. There's no covalent interaction here. It's just attracted to. As it, remember, positives, being attracted to each other. So the hydrogen attracted to the oxygen. Notice, though, how things are oriented. The positive-ish of the lower water is going to repel the positive-ish hydrogens of the upper water molecule. So they will orient themselves in specific ways. Also notice in B, the distance in these bonds. A covalent bond, 0.0965 nanometers. Okay? Compare that to the hydrogen bond, 0.177. It is almost twice the distance of a covalent bond. So 2 atoms that are covalently bonded together are going to be in a tighter radius, a tighter distance to each other than 2 atoms that happen to be hydrogen bonding from different molecules. Now, since the distance of this hydrogen bond is so great compared to a covalent bond, since there's no, actual interaction or exchanging of electrons, this association, easy to make, easy to break. Hence, if you look here at the dissociation energy, about 23 kilojoules per mole. I know that sounds like a lot, 23, wow. But if you go and you look it up and you see what it takes to break a carbon-carbon covalent bond, it's going to be 10 to 15 times higher amount of dissociation energy required to break that bond. So it takes that much energy to make it, takes that much energy to break it. So when you go through and you look, carbon-carbon bonds, carbon-oxygen bonds, carbon-nitrogen bonds, those bonds are going to be 1 log greater, 10 times at least greater in their required dissociation energy level. So because of this low energy required to break, it also means low energy to make. Thus, easy to make, easy to break, as I've already said multiple times already. So, in that given instant, in whatever volume of water you want to say, in one of your cells, in that cup of water, that soda sitting in front of you, whatever, that given instant, trillions of water bonds formed, trillions of water bonds broke and reformed. Trillions, trillions. Just keep making and breaking, on and on and on. It is not a set in stone. Once they associate, they will never be removed. And when you look at it here in this figure, what you see here when you look is that the water molecules associate with each other in such a way they maintain that orientation, that hydrogen, oxygen, that hydrogen for that oxygen are pointing away. Well, it allows that hydrogens that are pointing away to now associate with others. They theorize that for every 1 water molecule, it is hydrogen bonding with 3.4, depending on which textbook, whatever you want to read, 3.4 other water molecules. And again, made, broke, remade. Made, broke, remade. Over and over, constantly. Now, because liquid water, the water molecules are moving, they're vibrating, this aids in the making and the remaking of those hydrogen bonds and the chaoticness of it, hence the 3.4 on average. But when you pull out the thermal energy, basically you start lowering the temperature. You bring it down to freezing. That vibrations start to slow down. Water starts to line up, orient itself in a more rigid format. Hence, water molecules and ice can form 4 hydrogen bonds on average. Now, this making and breaking, constantly making and revamping the hydrogen bonds, gives water this neat attribute that it can absorb a lot of energy. I mean, if you look here, going from solid to liquid, basically ice melting, increase 5.9 kilojoules per mole. It's not a lot. It doesn't take that spacing, that going from one phase to the next here, that jump, that leap. It's actually more of just a small little skip. Couple degrees Celsius, couple of degrees Fahrenheit, whichever. You add in just a little bit more energy, ice melts. But once it's in liquid, look at that. You go from 1 or 2 degrees Celsius, you now have to get up to close to 98, 99 degrees Celsius before you hit that 100 where it's truly boiling, water boiling and giving up quite a bit of its volume as steam. Very few other liquids out there have this range as we see with water. What's interesting is water not only hydrogen bonds with itself, but hydrogen bonds whatever's within it, whatever solute is in it, and using it as a solvent, as long as there are polar or charged atoms within that molecule. As you see here along the figure along the bottom here. The OH at the bottom is supposed to be from, water, the hydrogen donor. But as you get over here to the right, you'll see it doesn't always have to be water. It can be hydrogen that's in pretty much any organic compound. The only times we do not see this hydrogen bonding in effect is when the hydrogen is covalently bonded to carbon, because then it's going to be a true non-polar covalent bond. Whereas with nitrogen, oxygen, there is going to be some polarity to it. Thus, it's going to allow hydrogen bonding to occur. Now, if you look here, the figures here, water is going to hydrogen bond with quite a few of the functional groups that you have learned in other courses. Hydroxyl, carbonyl. This is going to allow whatever those functional groups are attached to interact with water and thus have some solubility in water. Sometimes it's not even water. You look down here at the bottom here. Adenine and thymine, 2 nucleotides. The whole reason why your double helix holds together and is stable. It's because of all of these hydrogen bonds. Easy to make, yes. Easy to break, yes. But it's a cumulative effect. The more you have, the more stable those overall macromolecules can become. And it's interesting that these hydrogen bonds are not just one size fits all. The hydrogen bonds, even though the relative strength of them is going to be dependent upon bond angles. You look here to the far left. The strong bond is because of the orientation of the acceptor to the hydrogen from the, whatever the upper molecule is. Since they are in line with each other, it allows for a stronger association. You offset the lower molecule, whatever it is, it's still P double bond O, still probably part of a phosphate group. But because it's now offset and not in line with the upper, that hydroxyl group, whatever the R is, it could be water, it could be some other macromolecule. Because it is now offset, it will affect the hydrogen bond strength. And it's this interaction of water. How are things interacting? Is it a strong interaction? Is it a weak interaction? Is it only parts of the molecule are interacting? Hydrophilic, hydrophobic, amphipathic. Does it love water? Does it hate water? Or does it have a split personality and, it does both, depending upon which end or what part of the molecule you're talking about. Now, when you go and you look here at this table from the textbook, glucose can be considered polar because look at all those hydroxyls, all those OHs. They're going to want to hydrogen bond with water. Many of the amino acids, glycine, aspartate, are going to be polar, thus hydrophilic. They're going to want to interact. You're going to also have some things that are non-polar. Here, they're showing wax, but that could be any lipid, long hydrocarbons. A long carbon chain, whether it's linear as shown here with the wax, circular as a ring, doesn't matter. If it's carbon and just hydrogens, there's no charge there. There's no place where water can interact, thus nonpolar, thus hydrophobic. And then you're going to get many of our biologically important molecules are going to be what is referred to as amphipathic. They're going to be both polar, nonpolar, hydrophilic, hydrophobic, all within the same molecule. Phosphatidylcholine here at the bottom. Phosphatidylcholine is one of the forms of phospholipids that make up the membranes of all of your cells, of all of your organelles. You look here in the yellow portion there. That's hydrocarbon, thus nonpolar, thus very hydrophobic. But then you go up past the ester bond, the 3-carbon chain you see there, glycerol, go up, phosphate group. Above the phosphate group is an abridged amino acid. The phosphate group itself, I mean, you just look at it. It's got an oxygen with a negative mark. It's got a charge there. Anything charged, polar. Anything polar, hydrophilic. Hence, amphipathic. Hydrophilic head, hydrophobic tails. And hopefully you've seen this and discussed this in different courses. But the way water interacts with whatever solute is in it, as it's acting as a solvent, the water molecules are going to interact at the molecular level, as you see here with sodium and chloride. Remember, sodium and chloride are just bonded together by ionic interaction, a positive, negative attracting. The water will allow them to dissociate from each other, and then the water orients itself around either the chloride ion or the sodium ion in such a way that opposites attract. Notice at the top there. Chloride ion is hydrated because the negative chloride ion is interacting with the positive-ish hydrogens of water. And the reverse, the positive in sodium is interacting with the negative-ish ends of water, the oxygen. By forming around by forming themselves around, they are forming what is known as a hydration shell. They are now solubilized. Water has this ability, this attribute, to form what is referred to as dipoles. Hopefully you remember from Gen Chem 3 prior to organic, maybe inorganic if you've already had that. Dipoles are when something has 2 poles, north, south, or here, positive, negative. Well, remember, the oxygen at one side, the 2 hydrogens at the other, positive-ish, negative-ish, you have poles, hence dipoles. You have what's referred to as the dielectric constant. Okay? This dielectric constant, I believe that's E epsilon. It's not a ratio, it's a way of describing the relative dipoleness of a compound, a solution, a solvent, whatever. So as your book uses the example, benzene, which is nonpolar, has a constant that's at 4.6, whereas water, which is polar-ish, 78.5. So this, has no little milligrams per m, no kilojoules per blah, none of that. No, it's just 78.5. 4.6 compared to 78.5. It's just a means of comparison, a means of discussing the differences. What can we do with that? Okay, so we know the dielectric constant of water is a 78 point whatever. Well, We could take it a bit further if we go into physics. And we start discussing things. We want to sit there and discuss the interactions. In water, how are ions interacting? Okay. Well, if you want to sit there and discuss how ions interacting, first you got to discuss the size of the ions, the overall mass, the overall charge, if you will, of those, the magnitude of them. Then at what distance? Further apart, ionic charge, ionic interaction, not something we can measure, not something we really, it's there. Closer they get, the more the charge, the more they start to interact. Then you also have to take into account what solvent are they in. Different solvents are going to affect solutes differently, and vice versa. What solutes in the solvent is going to affect the dipoleness of the solvent. Look here at this equation. F, the ionic force between two things, is a ratio of the two magnitudes of ionicness, the charge for whatever one is, whatever two is, divided by their distance from each other, and the dipoleness of whatever solvent they are in. Hence the last slide, the 78 point whatever for water, the 4.6 for benzene. So we have a way to discuss, to measure how things are interacting in water. But how do we get the things into water? That's also something we also have to take into account. The solubility, not everything's going to be soluble in water, and things that are soluble in water, it's not going to be a one-size-fits-all. There's going to be some spectrum. Highly soluble, we can get it in, but it's going to take some work, soluble. And then everything in between. You look at some of the gases that you will find in water, in the environment, in your cells. Nitrogen, nonpolar, it's there, the nitrogen gas is there, but it's something that water, the body of water gives up relatively easily. It's not going to maintain it in solution. Hence the 0.018 grams per liter. Oxygen, I know it's weird, but to think about it, but oxygen's not that soluble either. I mean, it's kind of weird when you stop and think that there's, the majority of animals on this planet's history have been aquatic, since they need the oxygen in the water, but I guess that's how they get it out of the water so easily, is the fact that it's not that soluble. It's there, but it's relatively easy to give up. But as you go down that list here, carbon dioxide, ammonia, hydrogen sulfide, now you're polar. Hence, how do I know it's polar? Well, not only does it say it, but notice right there, the little delta negative, the delta positive, the nitrogen, the sulfur are acting like oxygen does in water, holding on to the electrons more often than not in that covalent bond. Solubility of oxygen, 0.035 grams per liter. Solubility of hydrogen sulfide, 1.8 kilograms per liter, 1,800 grams per liter. Makes a big difference. Polarity. Polarity influences solubility, which influences the ability of water to take it up and to hold on to it. Now, these nonpolar compounds interfere with hydrogen bonding, not only with themselves, but the surrounding water. So not only does the water affect what's been put into it, the solute, but the solute also affects the molecular water itself. Some slides ago, when I was talking about the sodium and the chloride, how the water allows the sodium and chloride to dissociate, and then the water surrounds each of the individual ions, forming that hydration shell. Well, if you take something even more that is nonpolar, put it into water, for the most part, yeah, it's going to float. Oil and water. Water and oil just don't mix. But you take much smaller things, much smaller macromolecules. You're able to disassociate them into the water more evenly instead of just pouring oil onto the water. What you'll see is that the water, it's not going to interact like we saw, sodium and chloride, but the water is going to interact with itself, and it's going to form what are referred to as clathrates. Clathrates is going to be this, well, let me just skip ahead. Clathrates is going to be this quote-unquote crystalline meshwork around that molecule. I mean, you look here. The artist's rendition of water interacting itself. Okay, you see hydrogen bonds being formed, made, broken, remade, whatever. But around that phospholipid there in the middle, you have the hydrophilic head, so water is interacting with that, no problem. But then you have that hydrocarbon. Carbon and hydrogens that, well, totally nonpolar, completely hydrophobic. So what you're going to see is this meshwork of the water molecules enveloping it, pseudo-solubilizing it. Okay. So what? So if you take enough of those little individual phospholipids, you've got that meshwork, that clathrate formation around it. You get enough of those forming. What's going to happen is the water molecules are actually going to push those together because of, close proximity. And instead of one with its own little clathrate, water mesh around it, and here's another one, and here's another one, they're going to start to associate closer with each other until instead of three individual, you now have one clathrate mesh surrounding three. Start bringing in more and more and more, and what you end up with is what's shown here at the bottom, a micelle. A micelle is a miniature bubble of phospholipids. The hydrophilic heads, the phospholipid heads, is pointing out, touching water. Hydrophobic tails pointed in. You see here in the middle here what's yellow, and there is absolutely no water present there. The water has been excluded. All of this you see here happens within seconds, milliseconds. Used to do this as a part of a lab when I was doing research. I wanted to study the trafficking of different lysosomes and stuff, so I had to make my own little vesicles to study how they're moved around. You take the phospholipids that have been dried and lyophilized, dump them into water, then seconds you have the beginning of micelles formed. You go and you agitate the micelles, and you get a bunch of those, thousands of those together in close proximity. You agitate them, sonic applicator, whatever heat. Instead of thousands of little micelles, they start boom, 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 bigger and bigger and bigger. Next thing you know, not only is the water on the outside, there's water on the inside, and you have a lipid bilayer. Oh, snap. That's a membrane. No work, no energy taken. It just happens. Then when you go and you look at things that are actually solubilized, say, as they're showing here, a substrate. The enzyme has its own hydration shell around it. We'll talk more about that can happen later. The substrate, it's got its own. And as they're brought closer and closer together, the problem is hydration shell, things can't touch. I mean, think about it. Visually, it looks like my hands are actually touching. But at the molecular level, there's water and lipids and all sorts of oils and stuff. So I'm not actually touching. Literally, I'm not actually touching hand to hand. Same thing here at the molecular level. So as the substrate gets closer to the enzyme, that hydration shell starts to dissociate. So now you've got this hydration shell with this gap, nothing there, and you now begin the interaction of the enzyme substrate together, the hydrogen bonding that's going to pull the substrate in further and allow for it to be positioned into an active site. And as it's pulled in, as the water is excluded between the two, not only you get the hydrogen bonding that's pulling in, and as it pulls in, the closer it gets, you start to see van der Waals interactions. Any two things you force close enough together will interact as long as you can get that water and all those other things out of the way. So if you can get them closer and closer together, two distinct things, substrate, enzyme, two proteins, two membranes, whatever. You get them close enough together, and you look at here, 0.11 nanometers, 0.15 nanometers. That's closer than a covalent bond, if you remember. There will be some interaction that will pull things in even closer. We got to keep in mind, though, everything we talk about here, hydrogen bonds, van der Waals interactions, things like that, hydrophobic effects, hydrophilic effects, these are relatively, quote-unquote, weak compared to a covalent bond. Covalent bond takes energy to make this. It's going to take energy to break. Hydrogen bonds? No. Ionic interactions? No. So the hydrogen bonds, easy to make, easy to break, constantly made, constantly broke, constantly remade in other ways, especially if we're talking water. The hydrophilic and hydrophobic effects, the van der Waals interactions. So what does this do for us in biochemistry, in cell biology? Well, as I said before in the intro lecture, many of the biomolecules we're going to be looking at are going to have some hydrophilic properties, but they're also going to have quite a few hydrophobic properties. The example here of an enzyme, protein. Not all amino acids, as you've seen, are going to be hydrophilic, are not going to be polar. Majority of them, or a lot of them, no, I'm not going to say majority, a lot of them, not so much. Non-polar, hydrophobic, or their interaction with water is going to be minimal at best. But you can't have a protein out of solution. Because it's out of solution, cannot interact with anything that is soluble. So, as you can see, proteins and things in your cells, even though technically they're not water soluble, there's enough solubility, enough water interaction that they will be forced, shoehorned into being soluble in the aqueous solution of the cytoplasm. Enough water interaction occurs that they found when they go and try to crystallize proteins to study the crystallography to get the three-dimensional structure, they have to still take into account the water that's going to associate with that protein, with whatever that compound is, that macromolecule, and it's going to form part of the crystalline structure, so they have to take that into account. Now what's interesting is that over the billions of years, we, and here I use the royal we as in the living we, all living cells have evolved enzymes, protein structures that utilize these attributes of water to further our metabolism or our metabolic reactions. So what's interesting is if you look at this picture here, in this pocket, this active site of an enzyme, all these different amino acids. Some are there for structure to help maintain that active site. Others actually have direct interaction with the water or the substrate. What you end up with is this series of water molecules that are not only hydrogen bonding with other water molecules, but are also being held in place by hydrogen bonding with the amino acids of that protein. I've mentioned it earlier in this lecture. Whatever solutes are present in a given solvent, they affect each other. Solute into different solvents will act differently. The solvent with different solutes, well, the solvent will act differently. We refer to this as collegiative properties. The collegiative properties of water. We know, you've learned since you were a kid. Water freezes at 0 degrees Celsius. Water boils at 100 degrees Celsius. Get those phase shifts. Different pressures, different this, different that. Unless you change what's in the water. You've heard the old wives' tale. Water freezes faster if it's hot water. Salt water doesn't freeze, things like that. Well, yeah. The properties of the water at that time, what's been dissolved in it, what its state is, will affect freezing point, melting point, boiling point, how much pressure, vapor pressure. Remember, vapor pressures at the, surface. Here's much water, here's air. Vapor pressure is how much, the atmosphere is pushing down, how much the atmosphere is pulling off of the water molecules, allowing them to go from the liquid to gas phase, evaporate, without the temperature of the water being close to the boiling point. We can go through and you can look at this in the lab. We can measure and use this as means to estimate osmotic pressures in cells, in organelles. We've actually developed a formula just for this. The osmotic pressure, and I forget what Greek letter that's supposed to be, mea culpa. What I, non-ionizing solutes, what's in the water. It's either 1 or 2. If there's non-ionizing or ionizing, 1, 2. The solute, how much of it's there, its concentration. The gas constant for whatever your solvent you're using. And then temperature. Because you always got to take into account temperature. Temperature affects pressure. The gas constant of the solvent will determine, not only its carrying capacity, how much solute can it handle, or also lets you know what pressure it's at. If it's high, if it's under high pressure, low pressure, 1 atmosphere, half an atmosphere, it makes a sense. And we also have to keep account that because of this, water moves. Your cells, the organelles within your cells, the cells within your tissues, the tissues within the organs, everything's in a constant flux. Everything is moving, and one of those things moving is water. Water's moving in, water's moving out. Osmosis. Which direction is it going to be moving? That's osmolarity. Well, that's what the whole Greek letter equals ICRT. That's just a means of determining osmolarity. Which direction is water going to move? And the movement of said water is osmosis.